You know that little black and white sticker sitting on your table right now? Yeah. Look past the simple surface for a second and try to see the glowing, high-stakes mathematical matrix hiding right in plain sight. Seriously, look around almost anywhere today. You'll see them on restaurant menus, train station turnstiles, payment apps, product packaging, you name it. I'm talking, of course, about QR codes. Most of us just lazily wave our phones at them, scan them in a fraction of a second, and totally move on with our day without thinking twice. But behind this simple, honestly kind of mundane action lies an absolutely extraordinary combination of advanced mathematics, computer vision, optics, and data encoding. In this explainer, we are unpacking the brilliant engineering hidden inside those little squares, because what you're actually doing when you scan one, you're triggering an absolute masterpiece of modern technology.
See, there's this massive gap between human perception and machine perception. To us, it looks like, I don't know, chaotic digital art or just a random jumble of pixels. But a machine's reality is entirely different. They don't see pictures in the human sense at all. They analyze strict, structured geometric patterns and binary logic. Every single tiny square inside that pattern carries specific vital information. It's a carefully engineered, machine-readable language designed for absolute precision and speed. The code is structured according to these incredibly strict mathematical rules that allow a scanner to instantly detect its orientation, figure out its size, and just start decoding. And honestly, it reveals something profound about how we interact with technology. Machines do not see images the way we do. They analyze mathematical patterns. QR technology, which, by the way, stands for quick response, and was actually invented way back in 1994 by a company called Denso Wave just to track car parts, is one of the absolute clearest demonstrations of how computers convert visual patterns into digital information. So, over the next few minutes, we're going to trace the exact millisecond journey of a digital scanning infiltration. We're going to see exactly how this visual math works. When you point your camera at one of these codes, it triggers a lightning-fast sequence. Boom. It happens in milliseconds, but it's an unbelievably complex maneuver. First, your camera instantly captures the scene, analyzing the bright and dark areas. Then it hunts for edges, looking for those strong, sharp transitions between black and white. From there, it mathematically flattens the perspective, and finally snaps a rigid grid over the pattern to sample the individual cells. It's an entire visual analysis pipeline, literally executing in the blink of an eye. But here's the thing. To even begin that sequence, the scanner has to make sense of the visual noise of the real world. I mean, imagine trying to spot a specific barcode in a crowded, brightly lit room while you're walking. It's chaos. To find the code in all that visual clutter, the scanner is specifically hunting for a navigation architecture to lock onto. It's looking for finder patterns, the quiet zone, timing patterns, and alignment patterns. These physical structures built right into the code are what tell the computer exactly how to read the data matrix embedded inside. You've definitely noticed those 3 giant squares in the corners, right? We call these the finder patterns, and they act as the ultimate anchor. They're easily the most recognizable part of any QR code, and their purpose is absolutely critical. They allow the software to instantly determine exactly where the QR code is, what its orientation is, the weird angle you might be holding your phone at, and the overall scale. Because of these 3 squares, the software can completely realign the image even if the code is rotated, tilted, super far away, or viewed entirely sideways. Now, right outside those finder patterns is something you've probably never even thought about. It's called the quiet zone. It literally just looks like empty white space surrounding the QR code, but this invisible white border is absolutely essential. The quiet zone helps scanners separate the QR code from any surrounding mess, like heavy text on a concert poster or the busy pattern on a restaurant table. Without this blank border, detection accuracy totally plummets. The scanner would struggle to figure out where the real world ends and the data begins. It's the perfect irony, really. Sometimes, absolute nothingness is your most crucial piece of data. Okay, so once the scanner finds the code and isolates it, it still has to deal with the messy physical world. Let's be honest, we usually haphazardly wave our phones at a weird angle over a curved soda bottle or a crumpled up receipt. To fix this chaotic geometry, smaller squares called alignment patterns trigger geometric transformations. The software uses AR-level mathematics, very similar to the tech used in augmented reality, 3D graphics, or even facial recognition, to mathematically reconstruct a perfect, flat square in the computer's memory. It completely negates your awkward camera angle. Once that image is perfectly aligned and flattened out, the system hacks right into the grid sampling phase. And this is where we get into the pure, beautiful logic of binary encoding. By turning visual light into a strict grid, the computer completely bypasses complex image processing and goes straight to raw binary data.
The scanner divides the QR code into a matrix of tiny cells, and every single one of those cells translates to the fundamental language of computing. It's so simple, yet so brilliant. A black square equals a binary 1. A white square equals a binary 0. The scanner is literally converting visual light and dark into a pure matrix of ones and zeros. So as the scanner sweeps across the grid, it ingests this raw stream of binary numbers. Just imagine ones and zeros flying by in milliseconds. But, a massive string of ones and zeros is completely useless on its own. The QR decoder's algorithm steps in to group these binary data points into meaningful chunks, all based on incredibly specific mathematical rules. And by grouping these binary matrices, it can compress and encode incredibly dense information. I mean, a standard linear barcode, like on a box of cereal, might only hold 20 to 30 characters. This two-dimensional binary grid, it can hold thousands. Those grouped chunks of binary instantly translate into the digital commands that literally run our modern world. In a fraction of a second, that visual matrix of black and white squares becomes a website link, a digital event ticket, a contact card, or even your Wi-Fi password. It instantly generates UPI payment requests or securely passes along login authentication tokens. The scanner successfully bridges that gap between a physical printed object and a lightning-fast, complex digital action. But here is a fascinating thought. How does the machine survive if the code gets compromised? We don't live in a perfect, pristine world. QR codes get scratched up, they get left out in the pouring rain, or someone sets a wet coffee mug right in the middle of them. If every single black and white square is a vital 1 or 0, shouldn't covering up a massive section of it completely destroy the information? How can your phone possibly read a URL if half the binary data is literally missing?
To solve this, the QR system deploys its absolute ultimate technique, and it's a personal favorite of mine, read-solemn error correction. This is a brilliant piece of complex mathematics that acts almost like a regenerative healing factor. When the QR code is generated, the algorithm uses advanced polynomial math to embed redundant backup data all throughout the matrix. Essentially, it plots the data points on a complex mathematical curve. If a giant coffee stain wipes out a chunk of that curve, the decoder uses the surviving data to calculate exactly where those missing points had to be. Think of it like a mathematically rigorous game of Sudoku. If you know the strict rules and you have enough of the remaining numbers, you can absolutely prove what the missing squares are. It's mind-blowing.
And because of this, QR codes actually support 4 different recovery levels, built right into their design. Level L can survive about 7% damage, level M hits 15%, level Q handles 25%, and level H can sustain a massive 30% data loss and still scan perfectly. This high level of mathematical redundancy is exactly why brands and marketers can safely drop custom logos or artwork right into the dead center of the grid. They are intentionally damaging the QR code with their logo, relying entirely on the heavy lifting of the Reed-Solomon error correction to mathematically heal that blocked binary data behind the scenes. What's truly wild is that this intense mathematical battle, the edge detection, the perspective correction, the binary decoding, and that complex polynomial error correction, it's all happening in fractions of a second. Modern QR scanners are astonishingly fast because our smartphones now pack incredibly powerful processors, the machine vision algorithms are highly optimized, and our cameras capture high-resolution images instantly. Some systems can even scan multiple codes simultaneously or read tiny, blurry codes from far away while you're literally walking past them. Now, stepping back from the math for a second, there is also a really clever architectural split in how these codes are actually used in the real world: static versus dynamic. Think of static codes like a locked vault holding permanently fixed information. If you encode a website URL into a static code, it can never change. That binary matrix is physically locked to that exact web address. Dynamic codes, however, act like a flexible digital switchboard. The QR code itself just stores a short, permanent redirect link. When you scan it, it pings a server that then routes you to the final URL. This means businesses can change the destination link on the fly for totally different marketing campaigns without ever having to print a single new QR code. And that kind of dynamic speed and reliability naturally evolved from being just a marketing tool into something that has utterly transformed digital finance. In countries like India, QR technology has mathematically removed the friction from financial transactions on a massive national scale. Instead of typing in account numbers, routing numbers, and confirming details manually, which is super prone to error, a single scan of a UPI or wallet app QR code instantly and securely transfers the merchant ID, the exact payment request, and the transaction details. It has effectively turned every single smartphone into an instant, highly secure point-of-sale terminal. But of course, this incredible convenience comes with a hidden catch. Because we humans suffer from total visual blindness when it comes to binary matrices. Again, we just see random squares. We basically have to blindly trust the code. And attackers absolutely know this. They can easily exploit our visual blindness by generating malicious QR codes that encode links to phishing pages, fake websites, or malware downloads. You might think you're just scanning a menu for a burger, but the mathematical matrix is actually routing your browser to a payment scam. This is exactly why modern smartphone cameras will now preview the decoded link on your screen, asking for your human confirmation before executing the digital command.
So where is this visual math going next? Well, the black and white squares we know today are really just the beginning. Researchers are actively exploring the next generation of visual mathematics. We're looking at the development of invisible QR codes printed with special inks, animated codes that constantly change their binary matrix over time for extra security, and highly integrated AR-linked QR systems. With AI-enhanced scanning and the inevitable rise of smart glasses, our wearable tech might soon interpret these invisible, ultra-dense, or even 3D QR structures in real time. It'll seamlessly overlay digital data onto our physical environment without us ever needing to pull out a phone.
The next time you scan one of these codes at a coffee shop or an airport or wherever, just take a second to realize what's actually happening. You aren't just taking a picture. You are triggering a literal masterpiece of computer vision, geometry, and binary math. You're watching a machine instantly decode a highly optimized visual language. And as this technology evolves to store vast amounts of data in invisible structures all around us, it really makes you wonder. As ultra-dense encoding continues to advance, what other hidden mathematical languages are already overlaying our physical reality, just waiting to be decoded?